Hello. Here's it for you. Thanks. Well, it's time. Welcome back, everyone. So we're very rapidly running out of weeks. Week 14 is going to be the last full instructional week. And when we go into the next week, 15, we're just finishing up any last topics and then immediately going into review mode for the final exam. But the other announcement is congratulations on getting through the third exam. The summary statistics, very brief summary statistics, are posted here. Just one more exam to get through. Well, any questions or comments at the moment?
Sorry. So will the final exam will be, or will it be cumulative or just taking up what we're learning in the next couple weeks?
It's going to be cumulative, yes. So it'll be a comprehensive cumulative exam. It's going to give an equal representation to all the topics we've covered that has an attached assignment. So I'm not going to give any like extra weight on section 8.2, 8.3. There may be just one question per those sections. As far as 8.4 goes, this is our last topic of the semester. I feel like we're probably going to finalize this one when we're back next week on Tuesday, which means I can't give a homework assignment for that because a homework assignment due on finals week is considered bad practice. So the final exam is also going to have an extra credit question related to section 8.4, so that if you study the problems you see here, there'll be a very similar type of problem on the final exam purely for extra credit. So because it's comprehensive and we covered not that many sections beyond exam three ends on 7.2. So we covered additionally 7.3, 7.4, H2, and 8.3. A really great sample final exam is just putting your exams 1, 2, 3 all back together. And I'll be posting additional sample exam problems for the sections that exam 3 did not include. Other questions about that so far? Okay, thanks for asking about that, George. And there's going to be some extra credit opportunities, one that's boxed out here that we'll talk a little bit more about on next week. My first extra credit opportunity out of two is really just kind of a sake of fairness. If, say, you had a rough exam, whether it was exam 1, 2, or 3, but you learned that material, you came back strong, the final exam can wipe out your minimum grade if the final exam grade is higher. So that way, say exam 2, maybe that one was just a rough patch. I think that one had quantifiers, which was tricky. If your final exam exceeds this minimum grade, say it's exam 2, it'll be a full on replacement. And this won't hurt your grade. So if your final exam grade is lower than the minimum, then you keep all just standard grades. And I'll post another extra credit opportunity that will be related to course evaluations, but as I understand, they're not open yet. So I'll probably discuss it when they are opened up, likely next week. Beyond that, since we're talking about the final exam, here's the information posted down here. I guess another kind of pseudo extra credit opportunity is late homework. If there's any section that you didn't complete, I'm going to accept it for full credit with the last day on Thursday, May 7th, pretty much the end of finals week. I'll be grading quite a lot on Friday potentially if you need to turn in a lot, but you're absolutely welcome to do so. And the official date, according to the registrar for the final exam, is on a Tuesday, May 5th, 12:30 p.m. to 2:30 p.m., a 2-hour exam. But I'm going to set this up pretty much the same way we've been doing for all of the exams in this class. It's going to be open between the 4th and the 7th, and that's really for everybody. So if the in-person section would like to take the exam in class at that time, I'll be here for the 2 solid hours. Even if no one shows up, I'll probably still be here, probably just grading something or doing something along those lines. The reason for that is there's again, a fairness issue between the in-person section and the online section. Online section, you can take it early all the way through Thursday. And for fairness with the in-person section, same opportunity to you as well. So if you just see a better day, if you have an exam conflict, anything like that going on, just let me know. I can send it off to the Idaho Falls Testing Center. Well, we'll post information down below here, just like we did on all the other exams. And this week is a busy one for me. Pretty much what's going to happen on Friday, after I complete all the grading, I'm going to start filling out more information, giving the exact coverage on this exam, really just a comprehensive exam up to section 8.3. I'll mention the extra credit question relative to that section 8.4, and I'll post sample exam problems down below just like we did before. Well, I think that's pretty much it for the major announcements at the moment. Unless there's any questions or comments at all, folks. Okay, well, let's jump into our essentially last official topic for the coverage of the final exam, making this one the last official homework assignment, 8.3. It's kind of an interesting section because, well, relations, I don't think there's too tough of a section. People are already handing in that homework. And from what I've seen, it doesn't seem like that one's too rough. Just an extension of what we mean by functions, taking off one of the uniqueness assumptions. But it gets dicey in this section, 8.3. Our ultimate goal is to discuss what an equivalence relation is, but it involves reflexivity, symmetry, and transitivity. And putting all of these properties on paper is actually quite a lot of work. So let's take our time through 8.3 and see how this goes. So first thing we're going to look into before even looking at those core definitions, reflexive and irreflexive being the first set, is a way to visualize all these definitions. They're highly technical. They're stated in terms of relations themselves. And if we can have a nice way to visualize a relation, it really helps internalize what these properties are saying in the very first place. So here's how we're going to visualize it. We have a relation R on a set A, meaning it's just a subset. And hang on, it should really say, just for full correctness, subset equals 2. I'm going to have to fix that. That should be R subset equals, there it goes. That's the correction there. Did not notice that symbol in my first read through. So the relation is going to be a subset. It could be the entire cross product, A cross A, on a single set A, and the directed graph is going to consist of arrows that go from A1 to A2 for every pair A1, A2 that's related, or every A1, A2 inside the relationship R as a set. So really all we're doing is visualizing differently than we did from 8.2, where in 8.2 we looked into a table. That's a great way to write the relation. Or you can just exhaustively list out all the elements. That's another way to write the relation in some cases. Or you can write out a set relationship property where here's the set membership condition. That's a fine way to visualize a relationship. And this is just going to be our next tool to look into what it does a relationship really look like if we visualize it differently. So essentially all we're going to do is, for example 1, write down the elements of the set, 3, 4, 5. You can write them in any way you like. There's a lot of artistic creativity that's available here. If it's 4 elements in the set, I think a triangle makes sense. So that's probably how I would write it in each one of these cases. Here we have a relationship on that set, a set of ordered pairs altogether, and we'll draw a directed arrow from A1 to A2 for every element that's related. This relationship is saying 3 is related to 5, so that means we'll draw an arrow going this way. Then that's pretty much the name of the game. Next one says 4 is related to 3, so we can encapsulate that relationship through that arrow there. 4 relates to 3 as a directed arrow. And then just similarly down the line, 5 is related to 4. They don't have to be entirely straight arrows, so if it makes sense to curve one for clarity, go ahead and do it. And some of them get a little bit weird, right? This one is saying 3 is related to 3. Well, we have to put down a directed arrow. Oftentimes we'll call this just a loop. So for here, use a loop. If 3 is related to itself, here's my loop to capture that. So that's another way to convey 3 is in the relationship. It looks like we have a loop at every one of these vertexes. So another one at 4, and another one at 5. So it's a weird looking relationship when you put it down all on paper. Not much more to say about this one, but just a different way to visualize what this set is trying to say as a relationship. We can see at a glance that every element is related to itself. And that's interesting in its own way because that's what we mean by reflexive. We can say that the relationship R is reflexive if for every element X in the set A, that target set here, we have that X is related to itself. And if the graph isn't too huge, if it's a small set like on example 1, then we could just see just by eyeballing it, this is a reflexive relationship. R is reflexive.
Quick question about this.
Yeah,
So I get reflexivity. For things like 3, 5, is it makes sense if 5 would be related to 3, but it doesn't seem the case here. So would it be closer to like 3 implies 5?
that's a good way to say it. Yeah. If 3 is first part of the relationship, it implies 5 is in the second part of that element there. And yeah, 5, 3 being missing is kind of weird, right? We looked at plenty of relationships already in 8.2 where that's not the case. Say, for example, the modulus relationship. If we had, say, 5, 0 in the relationship, 0, 5 is in there for sure. There was a lot of that kind of stuff. But that one turns out to be a relationship property of symmetry, whereas this one is just all about reflexivity. So yeah, we're coming into those properties. The arrow missing, meaning we don't have symmetry whatsoever in the set. So we can say R is not symmetric. Does that make sense for that comment there?
Yes, thank you.
Yep, absolutely. Well, we're pretty much again using the directed graph as just one big tool to process these new technical definitions. This relationship here happens to be reflexive. It's, hang on, I said not symmetric. Yeah, not symmetric. Sorry, I got mixed up with my properties. It's not symmetric, but we'll look into those properties next. Some relationships can be irreflexive. The only difference in the definition is we say a relationship is reflexive if for every element in the set A, we have the X is related to itself. Irreflexive is going to say for every X in the set A, we have X is not related to itself. And these are tricky definitions because this sounds like a dichotomy, but it is not. There is now a trichotomy. There are 3 possibilities. A relation can be reflexive, irreflexive, or none of the above. It could be potentially neither one of these at the same exact time. So our goal is just to take a look at,
Irreflexive. Sorry,
sorry, say again?
irreflective means that there are no entries where something relates to itself.
Exactly, yeah, not
Okay.
even a single one. So I guess probably the big word here to highlight is, let's highlight this differently. X and A, X and A. But logically, the big part of it is the for every. So if every single one of them doesn't relate back to itself, then and only then do we have irreflexivity. Another way to say it is no loops whatsoever on the elements. Other questions or comments at the moment?
And that loop only applies to itself because we have a sort of extended loop where 3 is related to 5 is related to 4 is related to 3. That doesn't.
This kind of loop going back in on itself. So starting at a vertex going right back to itself. Other questions at the moment? Okay, thanks for those questions so far. These are really the right kinds of questions to ask for this kind of stuff. And you can see already that this kind of material is really just intersecting a lot into graph theory itself. I mean, there's a graph, there's vertexes, we have edges going from some elements to the others. And so we're using this terminology pretty informally when we say just loop. But by loop, we specifically mean starting and ending at the same exact vertex. So now here's our goal for example two. We're going to draw 3 directed graphs on a set ABC, much like this particular one, 3, 4, 5. But what we want this time is we want relations R, S, and T on a set A, where R is reflexive, S is irreflexive, and T is neither reflexive nor irreflexive, just so that we have a mental image of what are the 3 possibilities in terms of this brand new definition here, which really introduces 2 properties all at once. So we already have a graph that's reflexive, so it's kind of a redo of what we did here. So let's just do a whole different one. There's lots of answers to this, so there could be many different takes, many different ways you decide to write this down. I go just as before, call this ABC. And for the relation R, we want R to be reflexive. That means, well, again, there's a lot of possibilities. The only thing that I have to do to ensure reflexivity is every element loops back in on itself. So if I do this, our job is done. That's automatically a reflexive relationship. It has just 3 ordered pairs. The set is A is related to A, B is related to B, C is related to C. So you can imagine there's a lot of creativity here. You could have done a lot more. You could have made an edge go from here, maybe let it come back. So A is related to B, B is related to A. You could have made an edge go this way and just leave it like that. However you want to write down this relationship is going to be just fine, as long as it satisfies that property, because R just had to be reflexive. So I'll leave it up to you again when you go to draw these for this kind of example, how you would like to draw it. It just has to hit that property. Oh, for the A right here. So we went around this A to match the A related to A property right here. And A being related to A was a loop that went like that. So we did go around A in that kind of way. Does that make sense for that question there? Yeah, absolutely. Well, if we want to change over to a different relationship, S, this one being irreflexive, again, you have a lot of creativity on how you might write down the points. You don't have to put them down on a triangle. You can put them down on any order. And how you build your relationship, totally up to you. Let's make it do something kind of similar to example 1. A relates to B, B relates to C, C relates to A, or you can change the order of those arrows and you have a whole different relationship altogether. But the moment we do something like this, I've made a mistake. Irreflective says for every element in the set A, B, C, we do not have that element is related to itself. So that breaks it. That is not going to be irreflexive unless we leave it just like that. There's no self-referencing loops whatsoever. So no reflexivity at any single point in another, that's saying it in another way. So this would be one way to write an irreflexive relationship. And again, you can make it pretty fancy. You can put in a lot of symmetry, making the arrows come back to each other like that if you wanted to. But you don't have to get too carried away. It's completely up to you how you'd want to write that down. So I'll make it be more simpler. Just to mention the major property, no loops on this one. And now if we want one that is neither reflexive or irreflexive, all we're doing is negating these properties. If it's not reflexive, that means there exists an element that doesn't relate to itself. And if at the same time it's not irreflexive, negate this, that means there exists another element that is related to itself. So one that is neither reflexive nor irreflexive will have a loop, but not a loop at every single vertex. So here is the relationship T, neither. Essentially, all we're again using is our logic on what these are really. These are just quantifiers. Negate these, and you've broken the definition. So if we go say A loops back in on itself, it's in no way irreflexive. There's a loop there. And if we just stop, maybe put in a couple more just to make it look interesting. Here's a couple more relationships. But now that I stop, I'm not going to put another arrow or another loop on here. It's not symmetric because not every element looped back in on itself any longer. So it didn't hit either one of these definitions because these are properties that say for every element in the set A. So T would have neither property whatsoever. Well,
Okay,
that's the rundown of the first set. Yeah, go ahead.
if this is out of scope, then that's fine. But um, we have these two logical statements, which in the earlier part of our class we could technically write as statements that we could prove or disprove, not necessarily
Mhm.
with the skills we have. But that implies there's a binary relationship, but we have this third possible case. Is there even a way to express that mathematically, or do we have to just see that um, uh, qualitatively that there is a third edge case?
We could write that down logically, I think is what you're saying there. Absolutely. So another way to re-express the case for neither, what we would say here is that T is, let's say, not reflexive and not irreflexive, which would then become logically equivalent to, I'm going to leave the and here, but move up, we're negating this. So we would say not reflexive means the existence of an element X and A such that X, X, we're negating this part of the quantified statement. We just didn't put in the for every, but you can imagine there absolutely is. You could rewrite it in quantifiers if you want to. Negation of that gives us the existential quantifier. Then negate this part and say XX is not an element of R. Then you go across the and. Here, we're negating irreflexive. So negating that means flip to an existential quantifier, exists X and A, such that negate that. Well, it's not an element of R, forcing it to be an element of R. So we say XX is an element of the set R. So writing down the property of neither in a quantified statement would really just be this. Is that what you were mentioning, by the way, George, in
Yeah,
writing it down this way?
yeah. So basically, this comes to down to definitions of our statements. Okay,
Exactly. And pretty much everything we do here in 8.6, you can recast in our chapter 3 with logic, with quantifiers, negating quantifiers, pretty much every single thing we did. It's just a new set of definitions we're throwing on top. We never touched on any of this way back in quantifiers because we just didn't have the material yet, basically. So yeah, thanks for mentioning that comment. Pretty much everything you see here, whether it's a neither case, reflexive, irreflexive, and with the symmetry properties, you can do the same exact kind of thing. And let's mention one more thing. The neither, really the critical thing was the and. Both of those things had to happen at the same exact time. The existence of an element in the relationship. Hang on, let me double check here. I think I did miss one thing. When we negated this part here, we had to negate here, which means not an element of. Let's put that in a strong color that really just shows up now that I missed that one. Reflexive means we found an element that's not related to itself. So sorry for the omission of the not an element of there. Here, that one was correct, but let's make it pop as well. We try to delete that. Sometimes things don't delete in the way you hope they would. There it goes. This one is in the set R. Well, our goal next is to just look into some interesting relationships, look through the definitions again, thinking in terms of what we did here, the visualization of what these properties are even saying, in terms of new and interesting relationships down below. So here's our example 3. For each one of the relationships, they're all given on the set Z. So the set A has been promoted to an infinite, countably infinite set Z. We want to determine if these relationships are reflexive, irreflexive, or neither. We'll explain, provide counterexamples where necessary. And again, this is where the problems can be sometimes deceptively tricky. There are a lot to these definitions, especially if you want to visualize neither. Look how big the condition becomes in pure logic. So here's 3 random scenarios. We want to determine properties reflexive, irreflexive, or neither on every single one. Well, let's start off on R1. It's an interesting relationship. Recall, when we say AB is inside this relationship, we mean both A and B came from the set Z, any integer, 0, positive, or negative. And to get inside the set, all that's required is that A is not equal to B whatsoever. Anyone see what kind of property this would have? Reflexive, irreflexive, or neither? Yeah, absolutely. This one turns into the irreflexive case. Recall, for irreflexive, we have to have for every element X in the set A, here A is Z, it cannot be related to itself. That means this is a proof, right? This is a for every statement. We're going to give a direct proof of this and say, let's make a statement first. R1 is irreflexive. Now we have to explain why, but the explain is just an honest proof. So let's say that, let's prove it. For every, what we do is we grab just an arbitrary element. Let's call it X, be in Z. Then we have to show X, comma X. X is not related to itself whatsoever. It's not in the relationship R. But to do that, we use the set membership condition. So this one's kind of a nice one, right? Well, the moment we pick an element X and Z, we can say then X is equal to X, but to get inside the set, for it to be related to itself, it had to have been not equal. Since X is equal to X, X comma X is not in the relationship R whatsoever. And we didn't pick a single X. We let it be any integer whatsoever. So we are matching up the for every when we say that. We can't, for example, do this problem by picking X is 5. We have to work in full generality to prove the for every statement. But the moment we have this for an arbitrary X, that's the end of the argument. We can maybe make the statement end right there or explain a little bit further. Since X is arbitrary, R is irreflexive. And the whole argument ends right at that spot. Well, we're done on that one. Any questions or thoughts, folks, on the irreflexive problem part here? Okay, it's a tricky problem in a certain way, right? we have a way to visualize what irreflexive really looks like, something like this. But that was a finite set. So what we have to do is try to make a mental image. If you did write down integers, say 1, 2, 3, 5, -1, -2, -3, -4, 5, I don't know why I skipped 4, with the understanding that they go on in infinite directions, you would note that there is no way to draw a loop back in on itself. It's a complicated relationship because if the elements are really not equal, you would have a directed segment going to every other element. So this is a massive relationship on the set Z. Let's go off to the next one. R2 is the statement that A plus B is even. You know, my gut would tell me that if you're looking into this kind of property, it's probably reflexive, but we have to explain exactly why. So here's the tricky part. We have to show that every element has to be related to itself. So it becomes kind of a definition crawl. We have to relate the definition of the relationship with the definition of what it means to be reflexive in the very first place. And so there's sometimes a good amount of stuff to say. So let's say R is reflexive. Let me just color code that so we can connect the dots on that. For R to be reflexive, we have to use this part. We must work in full generality. We have to pick an arbitrary element, once again, in the set Z. So let's say, for the proof, let X or A, however you'd like to call it. I like X because it doesn't conflict with the definition of the set using AB already. So I'll let X be in the set Z. Then how can we get X comma X inside the set R? How do we know X is related to itself? We have to add it with itself. We can say then X plus X. So I'm thinking of XX going here, but for XX to be in this set, you have to take the A plus the B, but A and B are the same. They're both X. So we're just looking into X plus X. X plus X, well, those are like terms for sure, so we can rewrite as 2X. But X was an integer, right? And if you're doubling an integer, we can go right back to our definitions from way back in the day, 4.3. We go back to the top on that. We're just looking into the definition of even. The value K is the value X right here. We have twice an integer for sure. So the original thing, X plus X, is definitely even, just strictly through that definition. Since, again, X was an integer. So we can say X plus X equals 2X is even. And so if the two things here come out as even, you put them together, XX. X is related to itself, so X comma X is in the relationship R. This worked for any integer X whatsoever. If you double an integer, this is essentially all this is boiling down to for reflexivity, then it's automatically even. And we essentially proved it by picking a generic X, adding it together, exhibiting the two to verify evenness. We can put here, since X is arbitrary, R is reflexive, but we knew it was arbitrary. That was our reason for just saying it be X, anything in Z. So we can end it here if you like and just say, this shows R is reflexive. So those are two interesting relationships also together. I think the not equals one is interesting if you think in terms of a graph. This one is just as interesting as well. And it's a weird proof because, again, we didn't do a whole lot with this. We just picked an element, show how it conveys with this set using the set membership condition right here, and get the even property. Well, any questions at all, folks, on part B? Okay, well, if one's irreflexive, one's reflexive, there's got to be a neither, right? So that's what we've got to do next. And here's the full formal definition using quantifiers of neither, neither reflexive nor irreflexive. Essentially, all we're doing here is we're going back to section 4.3. If this one's really neither, we have to disprove two things, or prove by giving a disproof. Or a faster way to say it is find a counterexample. If this relationship R3 is not symmetric, we must find a counterexample to symmetry. That's all this is saying. Find some x so that XX is not in the set R. And if it's also not irreflexive, we need another counterexample, and that's what this is saying. Irreflexive means we are going to be able to find some element that's related to itself under this definition here. So we have to give two counterexamples to show a neither. But again, I'm glad that question came up. Thanks for asking about it, George, because this is pretty much the structure we're trying to track through. So let's maybe carry that down and work it in our problem down below. We want to prove that this one is irreflexive, so let's just make the statement. And that was R2, forgot the subscripts there. R3 is irreflexive. So we can verify these in any order, but let's maybe start with reflexivity first. If it's irreflexive, then reflexivity's got to fail some way. So let's give our proof by counterexamples. Part one, we're verifying that we're not reflexive, so the negation of this. So let's say what we're doing here. We'll find a counterexample for reflexivity. So that means we have to find not a generic element X, we need a specific element. The set is Z, all integers, and we need just one integer that's going to negate before every condition here. Again, just essentially going for a counterexample. Anyone see what is one integer that would work? We could put both here and here, break that set membership property immediately.
0.
Yeah, good call. 0 is going to do the job immediately on this. So let's say, find a counterexample for reflexivity. Let X equal 0. So counterexamples are nice. We're not working in full generality. We just pick one example. If X is 0, we can say then we go back to the set membership condition. 0 times 0, well, that's equal to 0. And so 0 times 0 bigger than 0 is false. So we have a false on that set membership condition right there. As soon as false comes up, this means 0, 0 is not an element of the set R whatsoever. You can't put 0 next to each other. They won't be related through that specific property. The product had to be strictly non-negative. But 0, well, that's definitely, excuse me, I said that weird. It has to be strictly positive, and 0 is not positive. Well, that means we're just halfway done. We've only proven not that it's going to be, hang on, I want to say here, P3 is neither, is what I meant to say overall. I think I just got distracted on the properties. Meaning neither irreflexive nor symmetric. Excuse me, neither irreflexive or reflexive. Sorry, just a lot of properties swimming in my head. So we showed that the negation of this is true. There really exists an element. 0 does the job. Let's make our conclusion. This means R3 is not reflexive. Then we have to do the same thing all over again for irreflexive. And when we're looking for irreflexive, we need the existence of one integer, one number x, that relates back to itself. Actually, that one has a lot of examples, right? There's plenty of counterexamples. 10 would do the job. 1 would do the job. Let's go with a 1 because usually counterexample is nice when the number is simple. Let's say find a counterexample. For irreflexivity. The way this one will go is, well, we can say let x be 1. Then the major target we're looking at is this set membership condition here. If x is 1, then 1 times 1, that's absolutely positive. It's greater than 0. But the moment we have bigger than 0 on these two different integers means we have entered the set R3. So let's put a new statement. And so 1, 1 is an element of the set R3. But irreflexive meant you can never have the same entry here, the same thing related to itself. Let's take another look at that definition. It meant that couldn't happen. 1, 1 is not in the relationship. We just found a counterexample that shows it in fact is for this relationship R3. So now we can end the statement by saying this means R3 is not irreflexive. And that pretty much just ends the proof. That means it's neither. So our conclusion here, let's put a little border here. That's just our logic scratch work to help organize the thoughts. And our overall conclusion is now, therefore, R3 is neither symmetric nor
Reflexive, not
thank
symmetric.
you. That word just keeps popping in my head. Thanks for spotting that. It's neither reflexive, and I should just look down there. That would help my eyes. Neither reflexive nor irreflexive. So that's a pretty fast rundown. Took a little bit more time on part C. Some of them are faster than others for reflexivity, irreflexivity, and the case where it's neither property at all. Any last questions or thoughts, folks, going through any one of these? Okay, so that's our first roundup of properties. There's really 3 sets of properties in these notes. The reflexivity, irreflexivity properties. Next is going to be a collection of symmetry properties. And the final one is going to be transitivity. Transitivity is a little bit faster to get through, but seems to be traditional in just about every book on relations to do it in this specific order. Symmetry coming up next. And these definitions are kind of interesting. There's 3 definitions for symmetry. And just like before, it's not a trichotomy. There's 4 possible outcomes. Things could be symmetric, antisymmetric, asymmetric, or neither. Those are all possibilities. But you know, there's even more than 4 outcomes. Some of these properties can go together. Some of these are not exactly disjoint, just like in the last set. So you can write properties where, for example, asymmetric in fact implies antisymmetric. So asymmetric is just a stronger version of antisymmetric. And so a lot of these properties aren't necessarily disjoint outcomes for relations like we might think they are. These are very tricky in a certain sense. So just like before, let's work through these carefully, seeing what every single one of them is meaning. They're being hinted at quite a bit just in these notes as well, by just writing out our own directed graphs. Well, first, let's run through the definitions. We'll say a relationship is symmetric if, for every element in the set A, if you have a relationship, you can swap inputs and outputs. If AB is in R, then BA is in R as well. If we go back to section 8.2, this is like the canonical example of a nice relationship. It's both reflexive, symmetric, and transitive. It's reflexive because every first coordinate you see here is related to itself no matter what. But this property is saying if you swap the coordinates, 1, 6, you will see that 6, 1 is also in the relationship. If 1 is related to 6, congruent to mod 5, then 6 is also congruent to 1 mod 5. Plenty of relationships are not symmetric whatsoever. For example, this one, when we define the relationship where y is a moon of the planet X, if you swap the rows and columns, you have completely changed the meaning, and it's broken this idea here. So let's maybe start with a graph, a really fast graph, ABC, for symmetric relationship. Here's A, B, and C. And there are a lot of different ways to write a graph for this one. Let's write out, this is R, which is symmetric. So if I start out and put any edge that goes like this, that's A being related to B. We have to immediately backtrack and say, well, if that's the case, B is related to A, and so we have to do that. Put in a different directed arrow to convey those two elements here and here. If we stop, that's okay. This could be our relationship. It would just have two elements inside the relationship R. It had nothing to do with C. But if we do a little bit more, let's say take C is related to B. We have to reverse the direction, then B is related to C as well. One question we might have is, could we put a loop on it? Yeah, absolutely. In this, when it says A and A, B and B, that's to allow for both A and B to be different, but they can be the same. So if you let A and A be the same element here, or maybe let it be X, it'd be the statement that if X is in R, swap them, XX is still in R. That already implies something. Symmetric relationships are reflexive at this same exact time. So we can put loops on things like that to make it happen. Hang on, I take that back. It's possible to have a symmetric relationship that is not reflexive. Sorry, that was a misthought there. The reason being is you can have one loop, but there's no requirement to have a loop on every single element. Let me put that statement down. R being symmetric also says it's not required to be reflexive. So there's our symmetric relationship. Again, your version might be different. You might have a lot more loops, maybe C going to A and therefore A going to C. Well, other questions or comments so far with this one? Okay, again, these definitions, if you look at them closely, almost feels like they're repeating each other. Looking between anti-symmetric and asymmetric, these are pretty tricky definitions. So our job on these graphs is just to spot what is the key reason that one might be one and not another. So let's go next to anti-symmetric. Anti-symmetric says for every element in the set A and other element in the set B that are related, if we have a relationship A, B, and R, such that BA is also in R, it must mean that A has to be equal to B. So this one is now saying the only way you're ever allowed to switch the order of the elements inside this anti-symmetric relationship is if the elements were the same at the same exact time. That's the only way that this could be plausible. So that gives us a property to work with or think about right away. And here's our relationship. I guess that's going to be S for anti-symmetric.
So antisymmetric is perfectly reflexive.
Not necessarily. It depends on what we write down. Some of them would be, absolutely. But for it to be perfectly reflexive, there would have to be a loop at every single vertex. So it just depends on which one you draw. I think that's what was going to make me mixed up on this one right here when I was thinking in terms of symmetry. This one could be reflexive if we fill in loops at every vertex. So now it's perfectly reflexive as well, but it wasn't required to be for symmetric. And same kind of deal with antisymmetric. So if we put down vertices just like before, A, B, and C, antisymmetric says we can put an arrow that goes like this, for example. We can even put in a loop. A loop is absolutely allowed because the loop is saying, let's hover here on the loop. The loop is saying A is an element of this relationship S. And that's allowed because if you track through the definitions, if AA is an R and redundant, but you're allowed to do this logically, right? No one's going to stop you by tacking on another and statement where you switch A and A, but it looks like the same thing, AA and R. We have A equals A. So that allows for a loop, but we're just not required to put a loop on every single vertex. We could leave it off on B and C if we choose to for our particular example. So if we ended here, maybe put down one more arrow. This would do the job. It's antisymmetric, but we have a problem the moment we do this. Our definitions are in conflict if I put down anything that loops back from non-equal entries in the set. So I can't have B related to C. That'd be a B related to C here, and R, and then C going back to B, C going back to B, or C is related to B and R, because B is directly not the same element as C. So this arrow right here breaks antisymmetry. So to have true antisymmetry, we have to take that one off. We can put in as many loops as we want. Let's maybe put one more just to convey that. We put loops on everything, it's reflexive, but it could end just like this for our example. Any questions at all, folks, with the antisymmetric situation?
So anti-symmetry, you just can't do a back loop.
Exactly, yeah. If you go from B to C, no backtracking whatsoever. Loops are allowed, but that's it. Let's maybe put that on paper as well. One core thing about antisymmetric, it's not that loops are required at all, but loops are allowed. And by loops, specifically an element being related to itself in that kind of way. So now we have to look into what's different with asymmetric. And thinking in terms of how they wrote these definitions, again, they are pretty strange definitions in a certain sense. In the ordinary English language, antisymmetric versus asymmetric, they sound like they're synonyms, but these definitions mathematically are truly different. I want to also highlight this part, the for every. These are universally quantified statements, just like reflexivity, irreflexivity. And here's how this one goes. If A is an element of the set A, and B is an element of the set B for any one of those pair of elements, if AB, if A is related to B or AB is an R, then BA is not in the element set R whatsoever. Let's think about that. If A is related to B, then B cannot be related to A. In a certain way, that's what we were saying for antisymmetric, right? But these, again, it's a actually bona fide different property, truly. So spotting the difference is a little bit tricky. This one is essentially saying for antisymmetric, is that if A is related to B and B happens to be related to A, that happens in one condition, the entries were the same. And this one is saying it never happens at all. So this one is taking out all possibilities of loops whatsoever. Antisymmetric means no loops. The way they wrote the definition is parallel to what was written here. But if we think in terms of what we were saying here, it means if you let A equal B and then recast this definition, AB cannot be in the set R whatsoever, because if AB was in R, let me rewrite that as AA. AA cannot be in the set R whatsoever. A cannot be related to A, because if A is equal to B, and you said A is related to B, you're saying A is related to A, and then you could swap that. Nothing happens visually, but then the swap would happen here. You're saying AA is in R as well. So AA, forgot the slash there, is not allowed to be in the set R whatsoever. Let's make that null element pop. So what asymmetric is saying altogether is there are no loops that go backwards, and there are no closed loops whatsoever starting and ending at the same element whatsoever. So if we write something that goes like this, once again, this one's for the relationship T, anti-symmetric. Or excuse me, asymmetric. Let's go from A to B to C once again. If we have A is related to B, B is related to C, and let's maybe do something different just because we can. A is related to C as well. That would work. If something is related, we can never switch the order. None of these arrows go backwards whatsoever. And at the same time, for antisymmetric, no loops, such as AA specifically, are allowed. So that's what asymmetric would look like altogether. Well, there's lots of talk about just visualizing these three properties: symmetry, antisymmetry, asymmetric. So just a recap on all of them at once. Symmetric means the moment something is related to another element, you can switch inputs and outputs. So on the diagram, if there's an arrow going one way, it has to go the other way at the same time. And that allows for loops. Let's actually put that comment here. Loops are allowed. The moment you say anti-symmetric, that means if something is in the relationship and you do switch input outputs, it had to be the same input, same output. That allows for loops, but if A is related to B, these are discrete elements. B cannot be related to A, so no backtracking whatsoever for antisymmetric. And the only thing that's new when we say asymmetric feels like the same definition, but this is the new thing. You cannot have A related to A, similarly for B and C whatsoever. So no closed loops going back to the same element. Well, there's a fourth possibility that we want to put down on paper, and that is going to be a relationship V with neither property whatsoever. But before we put that down, any questions at all, folks, with the recap on these three?
I'm just having a hard time with anti-symmetry because if we have A equals B, can't we also have B equals A, which is the same thing as flipping them and
Yeah,
get that
absolutely.
back loop?
So if you're saying let A equal B, it's the same exact thing as B equals A. Then when we track through here, if we say A, B, and R, you're really just saying at the same time, AA is in the set R. If you look at this one, BA is in R. Well, they're all the same, right? BA is going to be equal to AB, which is equal to AA. So all of these are in the set R, which would imply A is equal to B.
Right, but doesn't that mean that we can loop backwards from B to A?
You could, but remember the B and the A are the same. So looping backwards just means that's all you're really doing.
Right, but if we go from B to C, why is it we can't go to from C to B if they're the same? If that makes sense.
So throwing in, say, a C, and you're saying you're going from, let me track through the comment there. We go through from B to C, and then, so that would be like this one going this direction, right?
Right.
But then if we say C goes to B is in R, that would be backtracking that way. But for anti-symmetry, it's saying the requirement is if that ever happens, B would have to be equal to C in the very first place. So in this diagram, that's impossible because B and C were meant to be discrete elements. These are specifically non-equal values.
Okay. Okay. It doesn't exactly make sense, but let's keep going and we'll see.
Gotcha. You know what might help out a little bit more is writing down the neither case. What's kind of interesting is sometimes these become a little bit more coherent in our mind of what they're all saying when you write down a relationship that has not a single one of the properties all at the same exact time. So let's try that out and come back to this property of anti-symmetry again. And we'll do just like we did before on the prior examples. Below, I have 4 random relationships. These are randomly sorted. So we're going to spot the ones that are neither symmetric, anti-symmetric, and asymmetric all at once in these various different sets of relations to further help with what the definitions are saying. But for one that's neither, might have to zoom in just a touch so we can see the definitions all at once. That's going to be the relationship V. None of these properties. It's still going to be a relationship on the set A, which has discrete elements A, B, C. And let's break these properties one at a time. And just to mention as well, if we wanted to, we could write none in the same kind of way. It would just be 3 things negated. So a second and statement, 3 properties where there's going to be an exist, an exist, an exist on every single one. Well, thinking in terms of just negating these once again, if we negate symmetry, that means we'll have that A is related to B. Let's just use this in the strict definition that's written in, not roted, that's a weird way to say that it's written in. And now if we want to break symmetry, we are going to disallow it to change order. So I am not going to make an arrow go backwards to A whatsoever. So if we leave that off, we now have broken symmetry. Let's maybe color code that. A is now related to B. But we're not going to put an arrow going backward whatsoever. So BA is not going to be in the set R. So this means not symmetric. So we'll resist the urge to loop back in that direction, meaning B not related to A. So that one's been killed. One problem destroys symmetry fully on this diagram. Next up, anti-symmetry. If we want to break anti-symmetry, that means we want to have this condition hold, and we negate this condition right here. Now let's think in terms of what we're doing in terms of formal logic. What's kind of fun about this section is we are very truly reviewing ordinary logic. And I wanted one more section I forgot to pull up. My section is going to be yeah, this one right here. So we're thinking in terms of negating this. And really, this is a if that holds, then that holds. There's a universal quantifier in front of it, but really it's just an implication. If this, then that. That means if you want to negate the implication, we've done that before. This right here, let's zoom in on that. To negate the implication, P implies Q, what we do is we assume P is true. We're going to allow these to hold. And at the same time, we're going to negate the Q, the conclusion. That means we negate this part. We make A actually not equal to B altogether. So if we want to break antisymmetric, we're breaking if this holds, then that holds, an if-then statement, which means just do that. That's the fast way to negate a kind of statement. So that's the logic point of view on this. That means all we have to do to break antisymmetry is say A is related to B is related to A, but ensure that A and B are distinct, not equals right at that one spot. So do that. Let's go. I'm going to use not A's and B's because they've already been taken up. Let's go from B to C. I missed. Let me try again. Go from B to C, and then go from C to B. But these are discrete elements. The set only shows the unique elements inside of it. B is not equal to C whatsoever. And so now that we have B is related to C, it's in the set R. C is related to B, it's in the set R. But B is not equal to C. We've broken this condition right here. Antisymmetry said whenever that occurs, they had to be equal. So we make a conclusion. B is not anti-symmetric. And this is where it kind of hurts my brain a little. That isn't double negation. You can't say not anti-symmetric means symmetric. That's not true either, because remember, this relationship is also not symmetric because we're not going to loop back to A on this whatsoever. So it's neither symmetric because of the purple arrow. It's not anti-symmetric, no double negation canceling there because of the blue arrows. And now we want to break asymmetry at the same exact time. But any questions or comments so far to this stage? Okay, so let's do that, just that. Let's break asymmetry. You know, kind of the hint is about loops. Loops were allowed for antisymmetric, but if you want it to be asymmetric, you cannot put a loop on it. So put a loop on any single element you want. Let's put it on just say A because visually it'll show up probably the best. A is now related to A. Now, what's the problem? If A relates to A, let's maybe just rewrite this comment for clarity. We're looking into this information here. Tricky thing about the definitions is when you say A and A, B and A, you're allowing the A and B to be different, but they can in fact be the same. We're allowing for any possibility on A and B. So if we do something like this, A is related to itself. It's in the relationship V. Sorry, I got confused on the lettering here. I put R, and that should have been a V. In several places. Sorry for the backtrack here. It's not used to writing down V as a relationship. Okay, going back to this right here, we'll say A equals B in A. So you can have A related to B, but if A is related to B, that means A is related to A is in R. So if that happens, if A is related to A, that means B comma A, well, A is equal to B, right? You can just rewrite B comma A as A comma A is in R as well, but it wasn't allowed to be. BA is now in R, but anti-symmetry, excuse me, asymmetry says BA cannot be in R whatsoever. So the moment you create a loop, if AA is in B, a loop, this means V is not asymmetric. So this particular relationship here, we can write down all the ordered pairs if we'd like to, fails every single symmetry property all at once. There's lots to talk about with symmetry, but this is our first initial definition about it so far. Any thoughts or comments at the moment?
Okay, I think I figured out anti-symmetry. So it would be like a function, some value is less than or equal to the next value. So B could be equal to itself or less than C, but C cannot be less than B.
Yeah, that's a great way to say it. So for anti-symmetric, we can say less than or equals to is a great example. Thanks for mentioning that. Yeah, that's a great way to think about it. And again, we're going to be taking a look at those when we look at these relationships down below. Notice I have a strict less than relationship here, so that's already kind of a hint on what this one could be. Modulus 5 is going to be a revisit, but we'll also look at the division relationship and subsetting relationship as well, in view of what properties do they have. At the moment, this kind of just looks like it's a weird kind of mathematical trivia, but this computer science importance of all of this is the moment we defined what we meant by cross products, way back in section 2, that was sequences, we already have a pretty big example of what cross products are all about. Things like relationship databases, the structured query language deals with cross products. And if you really want to work with these kind of languages more, you are having to deal with these kind of properties. So these kind of properties are key and important. From the mathematical side, what we're trying to build from all of this is a generality of what we even mean by the word equals to. If we take a relationship that is reflexive, symmetric, that one symmetric, and transitive, we can generalize the idea of equals to. If we want to generalize the idea of less than or less than or equals to, just take a different constellation of properties here, different properties like anti-symmetry, and you can have a generalization of less than or equals to, the so-called orderings and total orderings. So what all this stuff is trying to get into is really an extension of things we know well from algebra, like equality. We can extend that to a different kind of landscape, inequalities, and it has lots of practical computer science uses as well. I think that's worth mentioning because this feels like just strange mathematical trivia. It looks more important when you do it in these examples, like we're going to see below. But the importance of these kind of properties just really cannot be understated. This is a pretty big deal to mathematics and computer science all at once. What we'll do when we come back on Thursday's class is run through these definitions here. Transitivity is going to be a little bit quicker. The symmetry properties is really kind of the tricky part of the notes. Once we do that, we'll spend some time on the end of Thursday's class discussing equivalence relations. I don't want to spend too much time on our week 15, so we'll finish up our discussion on equivalence relations on the next week and then converge into reviewing for the final. So we're just about there. But any last questions or thoughts, folks, before we call today? Okay, well, have a great afternoon, folks. Thanks for all the questions and comments on these notes. These were very engaging and just the right kind of questions you'd want to ask when you see this kind of material. But we'll be back to it next time. Take care.